Good evening and welcome to week 8 of the live sessions. It is 6 p.m., but participants are yet to join. So we will wait for a few more minutes before we get started. Thank you. Good evening and welcome to week 8 of the live sessions for the NPTEL course on Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sajan Kapli, who is a member of the faculty of the Department of Mechanical Engineering at IIT Guwahati, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. Last week, we looked at some wire-based additive manufacturing processes, specifically shape deposition modeling or SDM process. Before that, we have looked at sheet-based AM processes, liquid feedstock-based AM processes. The topics we'll mostly be dealing with today are MIG-WAM, that is metal inert gas wire and arc additive manufacturing, and TIG-WAM, which is tungsten inert gas wire and arc additive manufacturing. We'll be looking at basics of the deposition process, cold metal transfer, process cycle, the important process parameters, modeling mostly of the geometry of a single bead, and then multi-beads along the Z plane. Also along the XY plane, we'll be looking at why there are some peculiar variations in material properties and some of the common defects. As usual, our sub-process breakup shows that metal wire additive manufacturing processes you deposit metal as the build material. The flow of material is continuous. However, recently there has been a surge of reports where people have explored drop by drop metal wire additive as well, and it has certain advantages. Do check them out in the published literature. The machine kinematics is mostly hybrid, and energy sources we are concentrated entirely on arc for the purpose of today. And as usual, typically we'll want to say eliminate the need for any supports. That can either be done through say careful orientation, or in case of say very simple geometries you don't need a support structure at all, or otherwise if the build geometry says that it will require support structure such as a hollow sphere, we'll make use of multi-axis kinematics, where either we can use say a multi-degree of freedom table such as a 5-axis CNC machine, or we can also use a robotic arm with say 6 degrees of freedom. However, there are some subtle differences between the two, which we'll also be looking at today. Before getting into worm, it will just be nice to revise the concept of an arc and what it is. Even though, say, most of us belonging to mechanical engineering and allied fields would have been exposed at some point to arc-based welding processes. We know that typically, say, the flow of electric current through a wire is through the metallic core of that wire, whereas the outer covering or the insulation uh, has the function of insulating the surroundings, that is for limiting the path of the current to the wire only. What happens if this covering is taken off? If the current that is flowing has say a moderate magnitude, or if the voltage drop across the two ends of the wire are not very large, the electric current will still continue to flow uh, through the wire only. But if the amount of current that the wire is carrying, or if the voltage drop across the two ends of the wire is very large, in that case, certain effects may transpire. If the voltage drop is very large, or the current that is flowing is very large, what can happen is the surrounding area, which say in is generally an insulative, uh, may become conductive. The electrons of the neighboring air may begin to move freely, and as a result, air might start to conduct electricity. And the path through air may in fact offer less resistance to the flow of current than the path through the wire itself. And in such cases, the arc is visibly formed. And that arc can subject the surrounding material to very high temperature. For instance, I mean, it is not uncommon for arc temperatures to reach some 6500 degrees Celsius or similar. And as we can see, it is clearly sufficient for melting and deposition of metals. This mechanism of arc formation is leveraged in processes like MIG-based worm and TIG-based worm, which we'll be looking at today. Now, for the first metal inert gas based worm, MIG welding gun is used to add material on a substrate or pre-built layer. It is also more commonly known as gas metal arc welding or GMO welding, where the one of the electrodes is a consumable electrode. This is nothing but the wire itself, and some similar processes are also flux cored arc welding, all of which can be termed in the MIG. And a typical setup for the MIG process is shown to the right here, where we have this wire feeder, which is pulled up here and which feeds the wire to the system at a particular tension and at a particular feeding rate, which are of course moderated by this deposition controller. We have the welding gun here, which has a copper nozzle. At the base of this copper nozzle, here we can see that the arc is forming from the wire. And because of the formation of that arc, high temperatures are achieved, which lead to local melting of the metal, both of the wire, which acts as the consumable electrode, as well as of the substrate or the pre-deposited layer. The CNC controller controls the movement of this bed. And on the left here, we also have the shielding gas reservoir, typically in the form of a cylinder, which continuously provides a flow of shielding gas, which shields the molten metal from contaminants, atmospheric oxidation, and similar effects. The consumable electrode in this case, as we saw, is in the form of the wire rail, which is fed at not necessarily a constant but at a controlled rate and through the feed rollers. The welding torch is connected to the gas supply cylinder, which provides the necessary inert gas. Typically it will be argon, but there are studies where they have varied the composition, the type, or even the composition. Say it need not be one single inert gas, it can be a mixture of them in some particular ratio. And studies have evaluated how changing the inert gas changes the deposition characteristics. The electrode and the workpiece are connected to the welding power supply. This can be an DC supply or an AC supply, as we'll see. And the power supply are always of the constant voltage type. As in, irrespective of whether it is DC or AC, the voltage itself does not change. The polarity may switch in case of AC. The current from the welding machine is changed by the rate of feeding of the electrode wire. And in fact, this is an important distinguishing factor between MIG-based worm and TIG-based worm. In MIG, the wire feed rate and the current are dependent on each other, they are interlinked. Whereas in TIG, both of these things, that is the current which is flowing through the wire or the current which is flowing into the system, leading to the formation of arc, and the wire feeding rate, they are independent. Now, the main requirement in a worm system is the source of electric power, because this is what will give rise to localized heating, which will lead to melting of metal and creation of melt pool. And these can be of two types: AC types or alternating current type and direct current type. DC arc welding is generally preferred because of the control of heat input offered by it. About 70% of the heat is liberated near the anode in DC polarity. Thus, if we want to have more heat input into the substrate, such as in this case here, case A, we want a deeper weld or a deeper deposition, a higher dilution. In this case, we will make the substrate into the anode and the consumable wire can be made as the cathode. And then 70% of the heat will be liberated near this substrate. And so we can expect a deeper weld. If more heat is required at the workpiece side, the workpiece can be made as anode, liberating a large amount of heat near it. And this configuration is referred to as the straight polarity or direct current electrode negative type configuration. If for some particular configuration we want less heat on the substrate, such as if we have a very thin substrate, or if we want to minimize the width of the heat affected zone which forms, or we want less penetration for any other reason, the polarity can be reversed by making the workpiece as negative, and this is termed as reverse polarity or direct current electrode positive. I may have messed up the signs here. Here the electrode is negative, and in this case the electrode will be positive. But this is for the case of DC. What about AC? For typically AC welding, the bead obtained will have somewhat of an intermediate characteristics between DCEN and DCEP. However, a particular use case for this AC based worm is when you are trying to deposit uh, materials which tend to oxidize very easily or which tend to form a protective oxide layer, which typically will have a higher melting temperature and more hardness than the base material. A common example of this can be, say, aluminum or aluminum based alloys. And there, in the case of AC, what will happen is for half of the cycle, the base metal or the substrate will be positively charged, and during this time, it will attract electrons from the wire, and these electrons, when they hit the surface oxide layer, they may be able to break the oxide. When the current is again reversed, a similar effect transpires where now the wire is positive and the substrate is negatively charged, and again from the base metal, electrons are attracted towards the wire, and they may be able to again break through the oxide layer and thus improve the build quality and remove the contaminant oxide layer which forms. However, because of this change of the polarity of the consumable electrode and the substrate every half cycle, the deposition characteristics that we see are somewhat intermediate, as in neither does it result in very deep nor very shallow deposition. In the MIG welding process, the filler material is transferred from the electron to the substrate, and depending on the current and voltage used for a given electrode, the metal transfer is done in different ways. It can be transferred via the short circuit transfer or dip transfer mechanism, or it can be transferred via globular transfer, where the material is molten and transferred in the form of, say, discrete globules. It can be transferred as a spray, and then again, the spray itself can either be pulsed or it can be rotating. And on the right here, we have this very useful table which lists the deposition rate uh, that can be achieved via these different metal transfer methods. As you can see, uh, it is arranged in a ascending order. Short circuit transfer offers the least amount of deposition rate, typically between zero point 0.9 to 2.7 kilograms per hour. And this gradually increases with globular and spray methods. In spray also, pulse spray tends to offer a slightly lower deposition rates, whereas rotating spray can deposit material to the tune of as much as 13.5 kilograms per hour, which is really impressive. And it is because of this high deposition rate of material, as well as the compatibility of the warm process, even with highly conductive or reflective materials such as copper and aluminum, that it is say acknowledged as a truly industrially scalable process. Because for industrial needs, we cannot always have methods like, say, selective laser melting, which will have very fine layers and very long print times. Of course, the other side of the coin is that because of these high deposition rates, the geometric accuracy is compromised. But then, with the advent of hybrid methods, where you also have subtractive, uh, say, cycles or subtractive options, sometimes in every layer, it can be taken care of. That is why wire arc additive manufacturing is a very attractive process. Now, the above are of course found to occur with varying rates of current, the lower rate giving the short circuit transfer mode, and the others are in ascending order of current as well. So, consequently, the metal deposition rate also increases in the order as shown. So, not only is this the order of increase of deposition rate, say m dot, it is also the order of increasing order of the current. And here we have, during the lecture, we could see videos of all of these different transfer mechanisms. In the case of short circuit metal transfer, what happens is the wire will gradually come in contact with the substrate. And because both of these will be part of some electric circuit, say in case of DC, if this is positive and this is negative, if they come in contact, it will result in a short circuit. And because of the short circuit, a large amount of current will pass almost instantaneously from the wire into the build plate. Thus, locally, this will lead to a very high temperatures, because as we know, joule heating is equal to I square RT. That is, it scales with the square of current. Because of this very high current which flows and the corresponding or the consequential very high temperatures which are achieved, this will lead to local melting, and the contact between the wire and the substrate will break, again breaking the short circuit. This process will repeat as more wire is fed, and it will continue depositing material, so on. In global metal transfer, instead of achieving short circuit, the metal is melted at the wire tip itself, and with increasing amount of current which flows and increasing temperatures, more amount of wire will continue to melt. After a point, this molten, say droplet of this droplet of molten wire will gain enough weight so that its weight will overcome the surface tension forces which were binding into the metal wire, and it will drop to the surface in the form of a small globule. Of course, with control of the process deposition process parameters, we can control the rate and the size of these globules. In spray metal transfer, instead of say large discrete globules, the metal is transferred to the substrate in the form of sprays or very fine droplets, and this is predominantly done with argon as the shielding gas. For pulse metal transfer, as we saw in the video, you can actually see bright and dark pulses. That is when the amount of current increases or decreases. And in this case, typically, the current is not constant. Rather, it will have some waveform which represents a pulse. Say for instance, if we are using a rectangular or square wave, we will have something called a background current and something called a peak current, and they serve different functions. The purpose of the background current in this case is to just maintain the arc. That is, once the arc is established, we do not want it to be extinguished. Because if the arc is extinguished, then locally there will be cooling, and it will take some time to, say, ignite the arc again. And there will be local cooling and heating cycles, which may lead to undesirable effects, as well as interruption of material deposition. The purpose of peak current is to melt the material. And so what we're essentially doing is we are maintaining some amount of background current so that the arc is never extinguished. Then, as per our given periodic waveform, we increase the current to some peak, melt the metal, and then decrease the current suddenly. During the holding time, the metal is transferred to the substrate or pre-built layer, and then this process continues in a pulsed fashion. And this is typically preferred because the materials deposited or built by this technique have good properties, good geometrical features, and so on. And thus, this is most suitable for warming. And then we have rotating metal spray transfer, where we are still transferring our material in the form of these spray droplets, but we also assign some form of a spiral motion to these droplets so that they spread around. Because of this spread, now the bead width is increased because the wire droplets are being spread across a wider region. But because of this spread, the energy which is contained in these beads is also spread around a wider area, and hence the dilution is smaller. Another say mechanism of material transfer is CMT, or cold metal transfer. And cold metal transfer MIG welding is one of the most preferable MIG welding processes due to low heat input characteristics. Now, cold does not really imply that it happens at room temperature or even lower temperatures. No, the material is still heated up. It's just that the amount of heat is very well regulated and less than some of the other techniques. The primary characteristic feature of CMT MIG welding is the alternating thermal arc pool. The melt pool is hot when the arc is initiated, and it is cold when the arc is extinguished and the wire is retracted. Initially, when the arc is initiated, such as in figure 1 here, the filler metal moves towards the melt pool, as indicated by this red arrow here. And here we can see the arc which has formed. As the current is less than the filler wire, the filler wire dips into the molten pool, and this leads to a short circuit and extinguishing of the arc, which is shown in figure 2 right here. Therefore, the welding current is lowered to a small value. A retracted motion of the wire then assists the droplet detachment in the short circuit. This is unlike the short circuit metal transfer mechanism which we saw in the previous slide, where the droplet is notched by a current impulse. It is because of the sudden rise in the current which leads to a rise in temperature, and that spike in temperature melts the material, breaking the contact. Here, the contact is broken by the retracting action of the wire, as we can see here. Again, as this distance increases, the arc can be established again, and once the desired gap is obtained, the wire motion is again reversed, and the process begins all over again. So, as we can see here, the motion of the wire is not really unidirectional. In cold metal transfer, the wire will keep getting fed back and forth. As we also saw in this video here, where we saw multiple cycles of this wire moving down and then up, down and then up, and we see this molten droplet of metal, which it transfers to this layer which is getting deposited. Just like all the other additive processes, even MIG-based BOM has our typical, say, levels of pre-processing, build process, and post-processing. Everything starts with a CAD model, then its conversion to an STL format, uh, giving it a proper orientation, checking for supports needed and generating those supports, slicing the geometry, and then generating a toolpath. Then during the deposition process, we can also have certain in situ processes which are not really deposition based, but which are, say, of a forming type or for enhancing the mechanical properties or maintaining the geometric accuracy of deposition, such as a rolling step, which can ensure proper bead height, or which can assign favorable microstructure and strength to the deposited layer. A short pinning or laser pinning step, which can introduce compressive residual stresses and can stress relieve the material. A hammering, where you can actually say pound the surface with a mechanical or pneumatic hammer. Or you can also have some interpass cooling, where, say, typically the time between layers is modulated, or we can have some other cooling mechanism. You can also have a face milling step, either for maintaining just the Z height accuracy, or say if we want a thinner uh, deposition uh, than the minimum bead width allowable by a process. In that case, we can face mill. And then we have the typical finishing processes, which might include milling, heat treatment, and then we get the final component. Now, it is important to understand that during the deposition, during the development of any such additive process, or even once the technology has been developed, then during the optimization of such a process, we have to move systematically. The most fundamental and key ideas emerge from single bead experiments, and I have seen even in 2025 people doing some very good research and drawing some very powerful insights just for fundamental single bead experiments. Once we have optimized our technology and the process parameters for a single bead, and by this I mean that we are able to achieve consistent, reproducible uh, bead widths and heights, stable deposition, no lack of fusion, or no balling phenomenon, good dilution, then we can say that our process parameters have been optimized for a single bead. The next step is to deposit beads adjacent to it. And it is not necessary that the same process parameters which were suitable for a single bead will also be suitable for multi-bead deposition. However, typically these single bead process parameters are good enough. Once this and typically what we'll be aiming to optimize in this multi-bead setup is mostly the hatch over distance, or the hatching distance, or the step over distance, which is the distance between the centers of these two adjacent beads. And depending on the type of surface finish we want, surface morphology that we want, whether we want it to be wavy or flat like or bulged, this distance can be varied. We can check whether there is any inter-track porosity forming, and what is the contact angle of the single bead from the substrate, whether it is concave or convex, and other things. Once our multi-bead parameters are also optimized, we can then go to a multi-layer deposit. And at this time, for a multi-layer, we'll be depositing some simple geometry like a cube or a cuboid. And only after this multi-layer geometry has also been optimized, that we can move to printing a full part or a component. At each of these stages, the most crucial process parameters which will be deciding the outcome of the print will be the power that you are feeding to the system based on the arc voltage, the starting, main, reduced, and final coordinates, the filler material, which will be the wire type based on the material composition, whether it has any contaminants, what is the percentage of impurities, whether it has any coating or coring, the diameter of the wire, which will typically be, say, 0.8 mm, 1 mm, or 1.2 mm. These are the typical welding wires which are available. And then the wire feed rate, as you also saw in MIG, the wire feed rate is inherently linked to the current also. These two go together. Then there is the inert gas. What is the composition of the gas? Whether it is argon or nitrogen. If it is a mix of two gases, what are the two gases being used and what is their proportion? What is the gas pressure, the gas flow rate? What was the gas free flow period? That is for how long we purged the chamber in case of a closed chamber, or the table if it is an open print. And how long after the build that we continue to make this gas flow? Because as we know, with the flow of this gas, we will have more better and more enhanced convective heat transfer. And so the cooling characteristics of the two will be different based on the period of flow of gas. Then the deposition parameters themselves, in terms of the layer thickness, the bead width, the bead height, then the torch characteristics, as in what was the distance between the nozzle and the base plate, typically called the standoff distance. What was the distance between the electrode contact tip and the base plate? Because for TIG based welding, as you will see, the uh, electrode and the wire are different. Therefore, the distance of between the wire and the substrate and the electrode and the substrate can be different. And the torch speed, or the speed of scanning or deposition. And then, of course, there is the path. That is what type of area filling method we are choosing, what is the step over increment, and so on. Now, some simple models have been presented during the course of this lecture, mostly modeling the geometry of a single beam. And here we start with the assumption that the portion of the bead above the substrate takes a parabolic shape, which is represented by this equation: y equals a plus cx square. Y is along the vertically upwards direction and x is along the transverse direction. The reason for this modeling is to establish the relationship across different process parameters and to be able to predict the bead geometry or the bead profile from the inputs that we give to the process. Uh, for the shape of the bead, which is assumed here, the parabolic bead, y equals a plus cx square. A is nothing but the height of the bead at the center line, and c is equal to 4h by w square, where w is half the width of the bead. And then the profile of the bead, y can be expressed as h times 1 minus 2x by w square. Now it is preferable to write the same parabola in terms of the process parameters, because as I said, the objective of this current exercise is to get or to be able to predict the bead geometry in terms of the input parameters, because those are the parameters that will provide as input and which we control. This is achieved by equating the expression of bead area obtained in terms of geometric and process parameters. Now for parabolic bead, the area, as we know, is 2/3 height into width, and in terms of process parameters, it can be obtained as 4d square Vw by 4 Vt, where Vw is the wire feed rate and Vt is the torch speed. And thus W can be obtained as equal to 3 pi Vw d square by 8h Vt. Thus the bead profile itself, y, is equal to h times 1 minus square of 16h Vt x by 3 pi Vw dw square. As we can see, bead formation is the interplay of several physical phenomena, such as gravitational force, electromagnetic forces, viscosity, capillary forces, thermocapillary forces, etc. Here, all of this physics has not been accounted for, and it is only a geometric model. Although both H and W depend only on the process parameters. Obtaining the relationship in terms of the process parameters alone is too difficult, as it would involve modeling all of these physical phenomena. Therefore, the above equation, which is a hybrid form of the parabola, includes easily measurable geometric parameter h, which is more useful. Again, we saw that in MIG welding, the wire feed is in synergy with the welding current. And most of the welding machines, it will follow a linear working curve such as the one given on the right here. And thus, even if we are not able to measure the current, what we could be measuring is the wire speed. And based on the working curves, we can then guess the current. Or in some machines, there may be no say way to measure the wire speed itself, but we can control and measure the current. And based on that, we can reduce the wire speed. Now, we can also model for multiple beads in the XY plane, which are still in a single layer, but now we are working with multiple beads. And here, the objective is that we want to have this flat surface between two beads, such as shown in this first figure here. And we can expect that with multiple beads getting deposited, the net effective surface will come out to be flat. Whereas in some of the other cases, this surface can be concave or convex, both of which are undesirable. And what the question we are asking is, what is that optimum step over distance which will allow for such a flat surface to be obtained? And this has been obtained with the assumption that the overlapping volume, which I am highlighting in red here, is equal to the volume of the valley, which I am highlighting in green. Only when these two volumes are equal, or in a cross section, only when these two areas are equal, will we have a flat deposition. And this is ascertained by equality of several areas. So for instance, area HGJ, which is this area right here, HGJ equal to area EFG, which is our primary assertion. Area HLG, which is half of it, is equal to area EIG, which is half of this bottom area, and area HLG is equal to area FIG, as these are both equal. And upon integrating within suitable limits, what we can obtain is the step over distance P necessary to achieve such a flat surface by equality of these two areas comes out to be 2/3 of the individual bead width. Thus, if we keep the step over distance equal to 2/3 of the width of one bead, we can expect to have a finished surface or printed surface which will be mostly flat. This has been taken from this work cited here at the bottom. I have not gone through this paper, so I'm not sure whether they also included some experimental validation or verification. But it will be really interesting to see if this works out. An example of the geometric modeling of MIG-WAM process has also been discussed here in the slides. And it says, in a MIG welding based WAM process, the following process parameters are considered, being the torch speed, the bead height, the penetration depth, the wire diameter, welding current, material density, and process efficiency. And we are asked to calculate certain quantities, those being the deposition rate in gram per minute, the bead width, the optimal value of step over, and the approximate value of the minimum power required. There are also certain helpful assumptions here that the bead cross section is parabolic, the working curve is given to us, relating the wire speed to the current, and some material properties are also available. The wire speed can be found directly from the working curve, because the welding current is given to us, which is 100 amperes. 100 amperes corresponds to a wire speed of approximately 8.4 meters per minute. And the deposition rate will be obtained from this continuity equation like relationship, where we have cross-sectional area of wire into velocity of wire times the density. This first quantity gives us the volume flow rate, and multiplied by the density gives us the mass flow rate. The cross-sectional area of the wire is already known because we know the diameter, which is 0.8 mm. The density is also known. What is known, not known? Okay, the wire feed speed is also known from this working curve. So we already know the deposition rate. The first part is done. Comes out to be 33 grams per minute. Similarly, we can find the bead width from our earlier relationships, which comes out to be approximately 4 mm. The optimal value of step over will be 2/3 of this, which approximately comes out to be 2.64 mm. And then the approximate power, yeah, the minimum value of power supplied to this will have two components, or there are two energy transactions in this process. One is for melting the wire itself, and the second is for melting the substrate. When we add these two and divide by the process efficiency, we can have a rough estimate of approximately 731.54 watts, which is the minimum power required. Similarly, geometric modeling can be done for multiple single tracks deposited one on top of the other along the build direction to form something like a thin wall. Some such structures are shown here, such as, for instance, on the first one, we have this hollow cylindrical wall of I think 1 layer thickness only. Then we have this hollow triangular column and a hollow square column. When we deposit the first bead on the substrate, the base is flat because our substrate is flat. However, once this initial bead has been deposited, every subsequent bead will encounter this first bead. The second bead will encounter the first, third will encounter the net effect of 1 and 2, and so on. In any case, for any of the subsequent beads, the base will not be flat. Therefore, the height and width of the bead deposited on the curved base has to be calculated so that the arc gap can be maintained throughout the process. One feature is to maintain the constant arc gap or the constant standoff distance, because our process has been optimized at some constant value of this arc gap or standoff distance. Another aspect is that say typically we will be provided with the final part geometry. Say you are to build just even if a simple geometry, and this height should be say 10 mm. When you deposit a single layer, you know that from your experiments, the height of this single layer is 1 mm. So to build this 10 mm block, will I just need to deposit 10 layers? Because typically what we find is the deposited height is less than the design height. Your slicing software will simply assume this to be true, and will not compensate for any, say, losses in height. And thus, it is very important to know what is the actual height of beads deposited far away from the substrate for building accurate geometries. Another aspect of, as we saw, is that we should know this distance so that we are able to maintain constant arc gap or constant standoff distance for maintaining isotropic properties. This has also been modeled, this time by assuming the profile of the deposited bead as part of a circle. Previously, it was assumed as part of a parabola. So the very first bead, which is getting deposited, will have its center somewhere inside the substrate as shown here. And the angle subtended by this sector on the center will be 2 theta 1, and we are interested in finding this red area marked A1. We can find the width of the bead and the height of the bead in terms of the radius of the circle and the angle which has been subtended. The width will become W1 equals 2R sine theta 1. The dilution depth will become R cos theta 1, and the height will become R times 1 minus cos theta 1. As I said, we are interested in finding the red hatched area A1, and this is seen to be some algebraic function of this blue triangle and this yellow sector. If we subtract twice this blue triangle from the yellow sector, we'll end up with area A1, and that is exactly what's done here. The area of the yellow sector, small a1, is equal to r square theta 1, which is just the formula for area of a sector. For the area of the blue triangle, it's half into base into height, since this is a right angle triangle. So we have half r sine theta 1 times r cos theta 1, which is equal to half r square sine theta 1 cos theta 1. Thus the area A1, which is this red area indicated here, is simply obtained as r square theta 1 minus sine theta 1 cos theta 1. We had already obtained W1 and H1 in terms of r and theta, and these can be fed here to find a relationship of theta in terms of these geometric properties, and that comes out to be theta 1 equals sine inverse of 4h1 W1 by 4h1 square plus W1 square. So we have theta also. Now, what about some bead which is deposited in between and far away from the substrate? And as we see very well represented here, the first bead is encountering a flat substrate, and the height, say some h1. Let us compare this with the height of some intermediate bead which has been deposited, say some h, which I have to call hn. You can see that hn will generally be small than h1, and thus it is very important to find what will be the height of these beads deposited far away from the substrate. It is reasonable to assume that for the same process parameters, the height of these various layers will be the same, just that they will be different from the very first layer which got deposited. And this has again been modeled here in this figure to the right, where we see that for the nth layer, the center is denoted by ON. For the n plus 1th layer, the center is denoted by ON plus 1. And the area of the bead deposited on top of the nth layer, that is for the n plus 1th bead, this area can be found as area EK FO EK FON plus 1 plus area EON FON plus 1 minus area ELFON. If we do this algebraic operation, we can find the area AN of this area hashed in black, and that is exactly what is done. So AN is equal to R square times pi minus theta n plus 4 into half R square sin theta n cos theta n minus R square theta n. Since the rate of material deposition is same in all of the beads, the area which we get should be the same. It's just that this area is spread differently, and so the height is smaller, but the area of material deposited will continue to be the same. It will just flow over the sides, which is why the height of the bead decreases. And this gives us an additional relationship where we have r square theta 1 minus sine theta 1 cos theta 1 equals r square pi minus theta n plus 4 into half r square sine theta n cos theta n minus r square theta n. And upon further simplification, this will give us the relationship sine theta n cos theta n minus theta n equals half theta 1 minus sine theta 1 cos theta 1 minus pi. While it may be difficult to solve this equation analytically, or a closed form solution may not even exist, it can be solved numerically. And through this numerical solution, we can obtain the values of theta n, which can be used to obtain the value of layer height. The value of the layer height HM, as shown here, is equal to the distance between ON and ON plus 1, which is nothing but 2r cos theta n. An example has also been solved here based on this modeling concept, which says a thin wall has to be built by MIG-based warm process. The single bead experiments first performed on a flat substrate. Assume a circular profile of the bead cross section and find out the height of the thin wall after deposition of 10 layers with the same process parameters. And here what we'll end up doing is find the layer of height of the first layer, then find the height of each of the next 9 layers and just add them to it. As we can see, this is the height of the first layer plus 9 layers of this second height, which gives us the total height. And see the difference between this. If all the layers had the same height as the first layer, we would have obtained after 10 layers a build of 20 mm, whereas in this case the actual build height is only 16.376. So we have almost 20 or 25% error in this case. Now, what about the variation in mechanical properties as we move along the build height of a part? On the left here we have a plot which shows the variation in hardness. As we keep going towards the top layers, the left axis indicates layer number. We see that there is an increase in hardness. Why does this happen? The hardness variation exists only in the final layers. It falls rapidly within thickness of a few layers, and for the first 12 layers, it is almost within the same range. It is spread across the narrow range. Then what happens in the final few layers? The hardness of the core is independent of the number of thermal cycles, because with increasing number of layers, the number of thermal cycles is decreasing. Where do these thermal cycles come from? Whenever a new layer of material is deposited, uh, it will be deposited at temperatures well above the melting temperature, and that temperature or that heat is conducted away from the melt pool through the previously built layers and the substrate, as well as there is some loss due to convection and radiation. When the pre-built layers conduct away this heat, the temperature there may also increase. In some cases, appreciably, even up to say that in the next immediate layer, it may even reach the melting point itself. And in the few layers below it, it can reach recrystallization temperature, or say even up to half of the melting point. These are the thermal cycles. Again, when the laser source or the energy source moves away, there is local cooling, which is very fast. And with the deposition of the next layer, or say multi beads in the same layer, there are successive heating and cooling cycles. Because of these solid state thermal cycles, the materials towards or the layers which are already deposited experience a large number of thermal cycles, which is equivalent to some sort of in situ heat treatment. Because of in situ heat treatment, the grains in these bottom layers become coarse, whereas towards the top they will be relatively finer. Of course, it's all relative to each other. And as we know from Hall-Petch relationship, finer grains tend to have higher hardness, whereas coarser grains, which form as a result of this intrinsic heat treatment, will have a lower hardness. This is the reason for variation of hardness along the build layers. Anisotropy is also seen in terms of other mechanical properties, such as tensile strength, and typically say you will assess the tensile property along the build direction, along the toss direction, along the step over direction to check for isotropy. Few specimens are prepared from each x, y, and z directions, and also prepared at some angle. And in one of the studies, it was shown that the z direction is weaker by about 20% in yield strength and 11% in ultimate strength. This was because of insufficient penetration or low dilution. Another correlation which has been shown between current or welding current and ultimate strength would suggest that with increasing welding current, the ultimate strength of the part also increases, as shown here in the plot to the left. Now let us discuss some of the defects in MIG-based bomb, and one of the principal defects is distortion due to residual stresses. Residual stress, as the name may signify, is the stress which remains in the part after removal of all external forces. And this residual stress in the part may lead to distortion of the part and hence loss of geometric accuracy. It also adversely affects the fatigue life of the part, which, as we know, has very critical applications. If the residual stress in the part is more than the ultimate strength itself, then cracks will occur. If the residual stress is less than the ultimate strength but still higher than the yield strength, then plastic deformation in the form of warping will occur. And for any fusion based process, because of the melting and solidification phenomena, it is close to impossible to eliminate the residual stresses from part produced by worm. However, the use of, say, intelligent tool path strategies or some post-build stress relieving cycles can significantly reduce the tensile stress. the residual stresses. These cannot be eliminated entirely, but they can be reduced to a significant extent. And to understand the generation of residual stresses in warm, two models are commonly proposed, those being the thermal gradient model and the cool down phase model. Now, I have not studied either of these and I'm not familiar with the warm process per se, but from what I can guess, these two models might try to understand the generation of residual stresses in terms of the thermal gradient, which say some particular layer or some particular region of material will experience because of melting and fusion in its neighborhood. And the second model can uh, discuss the same effects based on the cooling gradients or the cooling rates. And on the right here, we have this very helpful schematic which shows how these residual stresses are generated. So here we have this Gaussian energy source which leads to melting. The material inside the melt pool has molten, and as we know, typically metals will expand when they melt. Because of this expansion, the material which is surrounding this melt pool. So we are looking at it from the perspective of some material inside this substrate. This material will be subjected to compressive stresses because the melt pool is trying to expand. The surrounding solid substrate will try to resist this expansion, and so the substrate, some region of the substrate itself will be subjected to compressive forces, which is shown in this curve here. While the strains are still elastic, this deformation will be reversible. However, after a certain point, this will enter the plastic regime. The moment the stresses increase the, or sorry, go beyond the yield strength. Now, when the energy source has moved away and the local material which was initially molten now tries to solidify, metal when solidifying tends to contract. And with this contraction, it will also try to pull the surrounding material with it. Now, the surrounding material will experience a tensile force, which is shown here. And this tensile loading will happen parallelly with the compressive loading which is experienced before because the Young's modulus of the material will be the same. And now, when all the deformation has gone, there is this residual tensile strength, residual stress in the material, which is of a tensile nature. And as we know, tensile residual stresses can be very dangerous if there is some pre-existing crack in the part, which there will be in all cases. Some micro crack, a tensile residual stress will tend to open it up and make the crack propagate further. Whereas if there are compressive residual stresses in the part, they will tend to close this crack and prevent its propagation. Thus, it is very important that if we foresee a significant amount of residual stresses in our part, whether it is built by warm or some other fusion-based additive process, we should necessarily either change our toolpath strategy to reduce such residual stresses, or if that is not possible, we should definitely go for some post-build residual stress relieving methods, such as short peening, laser short peening, ball peening, or similar. Another common defect with the metal wire additive manufacturing process, such as MIG worms, is that of porosity. Porosity is another common defect observed in the parts produced by worm, and this porosity in the part will lead to component with low mechanical properties and low fatigue life, because pores are the regions where these fatigue cracks can nucleate. Porosities are broadly classified into two types: raw material induced, which are because of surface contamination of the wire, and process induced, which may be because of unstable process, uh, improper choice of deposition parameters due to poor path planning or contamination in the gas or something. As we'll see for say DAD or LPBF type process, the pores will be classified based on different criteria. There will be gas porosity or lack of fusion pores, but here they are classified as raw material induced and process induced. And some common strategies to control the porosity are AC MIG welding process or cold metal transfer, especially for aluminum and aluminum based alloys. The use of very high quality and pure shielding gas, and the use of non-organic piping, cleaning of the wire and substrate before deposition, high quality feedstock, optimal bead shape, that is, we want the contact angle if measured from within the bead to be acute. If it is obtuse, during the deposition of the next bead, there can be some region here which will be susceptible to porosity. Monitoring of the process and having some provision for live control where we can change the deposition parameters in real time to control the process, and post processing as well as in situ processing. Another type of another type of defect in MIG worm is the formation of cracks and the phenomenon of delamination. High temperature and material characteristics are the major reason for crack and delamination in parts produced by worm. And the two broad type of cracks which can occur are solidification crack, which is due to obstruction of solidified grain flow or high strains in the melt pool, and grain boundary cracking due to differences between boundary morphology and potential precipitate formation of dissolution. There are a few other types of cracks which are typically observed in fusion-based additive processes, such as ductilated dip cracking or liquefaction cracking. However, as I understand, they are outside the scope of the present course. Uh, Another thing which can happen is delamination between adjacent layers because of incomplete melting of the pre-built layer or substrate. This defect is typically visible and cannot be repaired by post-process treatments. To prevent this defect, pre-process or in-situ process treatments such as preheating needs to be considered. And here we have a qualitative estimation of the defects in various materials which are produced by worm corresponding to each color. We have titanium, aluminum, steel, nickel alloy, and bimetal. I'm not sure of what. And we have the common defects such as porosity, residual stresses, delamination, oxidation, cracking, surface strains. As we can see, bimetals are susceptible to residual stresses, deformation, and cracking, but hold up well against delamination, oxidation, and porosity. Titanium is very susceptible to oxidation, but not so much to others. Aluminum uh, is susceptible to porosity and deformation, as well as somewhat to cracking and oxidation, but it is resistant to delamination, and similarly for other materials processed via worm. Here we have a few examples of MIG-based worm machines, such as this one where this welding gun has been retrofitted onto a CNC machine. And we can also have 5-axis CNC-based MIG worm, where the need for support structures can be eliminated by tilting the table appropriately, so that the deposition head is always perpendicular to the layer which is to be printed. We can also have robotic MIG worm, where instead of a CNC machine retrofitted with a welding gun, we can fix the welding torch to a robot, and a robot with sufficiently high degrees of freedom can be used to deposit the structure. The rest of it, that is, the rest of the components are much the same. And here we have an example of MIG worm machine, incorporating parallel kinematics by the use of a delta robot. Similarly, hybrid kinematics can be used, and here we have a computer model of such a proposed machine. The other set of lectures for this week dealt with TIG worm or plasma worm. And tungsten inert gas welding or gas tungsten arc welding is an inert gas shielded arc welding process using non-consumable electrode. This is the primary difference between TIG and MIG. In MIG, the wire itself was the electrode, which was also getting consumed during the process. A typical tungsten inert gas welding setup is shown in the figure to the right, consisting of a welding torch at the center of which is this tungsten electrode shown in black. The non-consumable electrode creates an arc which creates a molten pool in the substrate or pre-built layer. The wire is fed from the side at some predefined angle. An inert gas is supplied to the welding zone through the annular path surrounding the tungsten electrode to effectively displace the atmosphere around the molten pool. A flare wire is fed towards the molten pool, which, after getting melted, deposits the material on the substrate or pre-built layer. And since the electrode and the wire are separate, in this process there is separate control over the wire feeding process and the current. The typical deposition rate in TIG worm is between 15 to 30 grams per minute. Because of the use of non-consumable electrode, typically a direct DCEN configuration where 70% of the energy is generated on the substrate or AC polarity is preferred. When a step pulse DC current is used, the current level is maintained at two levels as shown here, being background and peak currents. The low level is called the background current, which is used for cooling the deposited material, and the other is the peak current, used to melt the deposition material. Plasma cladding is somewhat similar to TIG because it also uses a non-consumable tungsten electrode to produce an arc at a workpiece. In TIG welding, the inert gas is used only for shielding. Whereas in plasma welding, the shielding gas is divided into two parts. Some of it flows into inner core for ionization and establishing the arc, and the rest of it flows into the outer core for shielding purpose. So here this tungsten electrode can have some annular channel, and some of the gas will flow inside and come out from this side, as we can see, and which is chiefly used for ionization and establishing the arc. There is a second part of this gas which comes from here as shown in green, which is actually used for shielding the melt pool and for displacing the oxygen and other atmospheric gases. Plasma is more popular in warm, as unlike TIG, in this case the tungsten is not projected outside and hence the bead height can be increased significantly. In the previous case, this tungsten electrode was projecting significantly outside of the nozzle, and because of this, the maximum bead height which could be printed was limited. Also, if we have poor process planning or poor process control, there is a chance of collision of this tungsten electrode with the built part. Whereas in this plasma cladding, this TIG is well inside the nozzle, so it may only come up to some partial distance and not fully outside. And so not only is the electrode safe, because of this we can also increase the height of the layer which is getting deposited. Here we have some typical setups using these principles. As we can see, the bright arc which is formed in the image to the left, and how this wire feeder comes from the side and feeds the wire at some specific angle. Here we have an example of a TIG or plasma based welding using a robotic arm in this case instead of a welding gun. Again, the wire is fed from the side at some specific angle, and inert atmosphere is maintained, and we see how this wall-like structure is getting deposited. Similar to MIG worm, in TIG worm also the crucial parameters for controlling the process are the power in terms of the arc voltage, the starting, main, reduced, and final currents, the filler material in terms of the wire type, its material composition, coating, coring, etc., wire diameter, wire feed rate, the gas, where the gas proportion, gas pressure, gas flow rate, gas pre-flow period, gas post-flow period are to be considered. The deposition parameters in terms of the layer thickness, the bead width, bead height, the torch, that is the distance between nozzle and base plate, distance between electrode contact tip and base plate, and the torch speed, as well as the area filling method. Uh, the material deposition can occur in one of three ways. It can occur in the form of droplets, where the material gets molten, breaks down into discrete droplets, and get deposited on top of the pre-built layer or the substrate. This is typically the case when the input power is very high, or the wire feeding speed is very slow, in which case adequate amount of wire does not come in interaction with the energy source, and so it breaks up into droplets. The other extreme end is wire plunging, where before the wire melts, it is plunged into the pre-deposited bead or the substrate. This can occur because of very high wire feed speeds or low energy input to the system. And of course, the optimum case is that of bridge transfer, where the power and the wire feed rate are so well tuned that the wire just melts as soon as it is approaching the pre-deposited layer, and the transfer of material happens continuously. The droplet landing position in TIG-based worm has also been modeled to have a more accurate system, and this was modeled under certain assumptions. The tip of the wire will be in the weld pool after molten drop formation, and hence tip of wire is assumed to be adiabatic, so there is no heat transfer from this phase. The shape of the arc is assumed to be Gaussian, so not just the power distribution, the shape itself is assumed to be bell-shaped. The height of the tip of the arc is same as the arc length. The arc column boundary is the position where 95% of the maximum heat flux occurs, and the drop falls vertically at the same location where the tip of the wire melts. It does not have any further travel, say due to Lorentz forces because of interaction with the electric field or so on. And these expressions that we see here, we are already familiar because we dealt with them during our study of laser in liquid-based AM processes. Since the distribution is assumed to be similar, Gaussian, the treatment is also similar, and so we can find the position of the molten bead depending on the amount of energy that is absorbed from the source. The heat absorbed by the tip can also be found, and thus it can be modeled. An example has also been worked out using this model. The defects in TIG-based worm, such as residual stresses, porosity, and crack and delamination, are similar in nature to those observed in MIG-based worm, but a critical difference in the two cases is that of omnidirectionality. In MIG-based worm, the wire was fed from the center, and thus irrespective of whichever direction we scanned, the wire always interacted with the substrate in the same way. That is, the relative motion of the wire and the substrate was the same. That is not true in this case because here the wire is always fed from the side at some specified angle. And let us see how it can be different. Here we see the four positions 0 degrees and then going clockwise 90 degrees, 180 degrees, 270 degrees, and then coming back to 360 degrees. So we can mark these positions as 1, 2, 3, and 4. In position 1, we see that the head is moving along the tangent to this black circle. At this point, it is moving downwards, and the wire is getting fed from one side. Thus, this is a case of side feeding. When the deposition head comes to position 2, it has still continued to move along tangent to this black circle, and at this point, it is moving leftwards. The orientation of the wire in the deposition head is fixed, and so the wire is still being fed from the side only. But now, because of the relative motion between the TIG head and the wire, at this point, it becomes a case of front feeding. At position 3, it is a case of side feeding again. And at position 4, now the TIG head is moving to the right, whereas the wire is also being fed to the right, and this it becomes a case of back feeding. Thus, we see that there is a difference in the relative motion between the wire being fed and the motion of the torch, depending on various positions, and this leads to deviations in the bead width and deviations in the bead height and a lack of isotropic properties. This is referred to as the lack of omnidirectionality, that is, the deposition characteristics will depend on the direction along which we are depositing or scanning. The term omnidirectional indicates an equal sensitivity of the process in all the directions. An omnidirectional antenna will send or receive signals equally well in all directions. For an omnidirectional AM process, the geometric or metallurgical properties of the fused layers are independent of the direction of movement of fusion source in the XY plane. And some of the proposed ideas to overcome this lack of omnidirectionality are shown here. One is feeding the wire feedstock coaxially with the fusion source, such as we saw in the case of milk process. Then using a coaxial fusion source surrounded by feedstock, which has been implemented for powder, where we have an annular feeding of powder, but may be difficult using wire feedstock. Then using coaxial feedstock surrounded by fusion source, which has been implemented where you have annular lasers or maybe approximated by a few discrete lasers, and you have the wire which is being fed coaxially, and we can dynamically adjust the feedstock feeding directions. Some such schematics are also shown here as to how the omnidirectionality can be achieved. And here we have a few examples of industrial scale parts printed using this TIG worm, such as in this case. We have an example of this titanium tank, which may be used as a pressure vessel and is truly of industrial scale. And that's why, as I was saying, worm is truly one of these processes which has shown enough potential and promise to be industrially scalable, as opposed to some of the other AM processes which offer very great control over the build geometry, but because of the long build times and the complexities involved, or the limitations in part volume which can be printed, are not really industrially scalable. So with that, we have revised the crucial concepts that were discussed this week. Let's break for a very short while, and when we return, we'll do some example problems to strengthen these concepts. Welcome back and thank you for your patience. Let us now proceed with doing a few example problems that will help us strengthen our concepts and will be useful for solving the assignment problems as well as for the course certification examination in case you have signed up for it. So just to uh, provide more insights into the thermal cycling aspect that we discussed in today's live session, I had modeled a simple direct energy deposition problem in a commercial package. And for the deposition of some simple geometry with a relatively coarser mesh, I looked at the temperature histories at a few nodes. We built 12 layers and I plotted the temperature history at every third node, which is shown here as N0, N3, N6, N9, and so on. And this is shown here. Uh, Here the maximum temperature was 1370 degree Celsius. The minimum was 38, somewhat close to ambient. And we have the thermal histories, temperature with respect to time for various layers, starting from layer 0 for 1, 2, 3, and 4 on the figure to the left, and in B we have it at every 3 layers. And we can see these small spikes or these small wiggles in the temperature history, and let us try to understand what they are. So if we come from the top down, that is if we start with layer 12, we see only this single spike in temperature close to 1370 degrees Celsius. And if we project it, then we see that this, okay, we see that this temperature spike is felt in all of the subsequent layers as well at the same time. For the ninth layer, again we see that there is a temperature spike corresponding to itself, layer 9 and 1 from 10. So this was from 12, 11. This is from the preceding layer, layer 10, and this is for the layer itself. So we see that with the deposition of the next layer, the temperature in this layer did go up to melting temperature, and so full melting can be expected in this layer as well. And this effect has also carried over onto all the other layers. And this is even better seen in this plot to the left, where I have plotted the thermal histories for all layers. We have the spike due to layer 4 and due to layer 5. Here, this is the effect of layer 4 on the third layer. This is the spike due to layer 3 itself. And for all successive, say 5, 6, 7, we see these small spikes in temperature. Now, in the present case, and again, this will carry over. So for the next one, we have 2, 3, and for the first layer, we have this is due to layer 0, so this is on the substrate. Now, we see that for the immediately preceding layer, the temperatures rise high enough to melt the material, whereas for the other layers, they may not go as high, but they can reach, say, around 450 degrees Celsius, which for certain materials may be enough to cause some solid state phase transformations. And this is the phenomenon of thermal cycling, that is, with the deposition of subsequent layers, one reference layer uh, can experience changes in its thermal history, or its thermal history is impacted by the deposition of subsequent layers. Now, let us look at a few example questions. The first question is asking us, in which of the following cases would an AC source of electric power be useful in the context of MIG-WORM? So as we remember from our discussion, in MIG-WORM the wire itself was one of the electrodes and the substrate was the other. In case of DC, they would have some assigned polarities. In case of AC, that polarity would change every half cycle. But what could be the reason for preferring AC source of power in some case? Is it to obtain an intermediate depth of penetration? And by intermediate, we will infer that it is between DCEP and DCEN. Yes, and this was seen to be true. It was used for cases where we wanted an intermediate depth of penetration. Is it for the deposition of metals which are easily oxidized? This is also true because as we saw, because of the reversal of polarity in an AC power source based MIG welding process, the oxide layer on the surface of the pre-deposited layer or the substrate can be broken up, which will allow for easier deposition of the wire material. Is it for reducing the overall power consumption? Uh, we do not have definitive knowledge or facts to say that this is true. We cannot conclusively say that by using AC source of electric power, the power consumption can be reduced overall. And so both A and B are correct. Yes, option D is the correct answer in this case. Question 2 is asking us uh, the functions of background current and peak current in pulsed metal transfer are to generate droplet of molten metal and to maintain arc respectively. The function of both of them is to generate the droplet of molten metal, to maintain arc and to generate droplet of molten metal respectively, and for both of them to maintain the arc. Now, if you remember, in pulsed metal transfer, instead of applying a constant current, we had some current wave. We used a square wave as an example, but it might just as well be anything. It's like a sinusoidal or triangular wave or anything. And here we had two levels of current. One was this background current and a higher peak current. And given that the peak current is higher than the background current, one thing we can be assured of is that it will give more power input to the system. And so it can be used for melting of the material. Because if the background current was sufficient to melt the material, there would have been no need to have a peak current. Because here we are not really bothered about the amount of superheat that can be supplied and any beneficial effects it may have. So the peak current, of course, is used to generate the droplet of molten material. But if background current also has the same function, then we can have just this constant peak current. The function of the background current, if you remember, was to maintain the arc and to prevent it from getting extinguished. So background current was used to maintain arc and peak current to generate droplet. And so option C is the correct answer. Question 3 is asking us, what changes are observed in the case of rotating spray metal transfer as compared to spray metal transfer? That is, the rotational concept is added here. And what advantages or disadvantages can it bring? Does it lead to decrease in the depth of penetration? Does the width of the bead decrease? Does the depth of penetration increase? Or does the width of bead increase? Now, if you remember from our discussion, in a rotating spray metal transfer, the metal droplets which are transferred in the form of a fine spray are additionally imparted a rotational motion which spreads the metal in the XY plane. So previously where they were getting deposited in a concentrated fashion directly below the MIG wire, now they will be spread out. Because of this spread, the width of the bead will increase. because now the material is getting deposited in a larger region. But the amount of energy being supplied is the same. So if the molten material is now spread along a wider region, the energy concentration per unit area is lower, and so the depth of penetration will decrease. And we have to look for the option where both of these are included. So we are looking for both 1 and 4. So option C is correct. Which of the following statements regarding residual stresses in a warm built part are true? Residual stresses are inevitable and cannot be avoided. Tensile residual stresses are preferable as they inhibit crack growth. Compressive residual stresses are preferable as they inhibit crack growth. And compressive residual stresses are more dangerous than tensile residual stresses. Let us examine each of these statements one by one to check whether they are true or not. Residual stresses are inevitable and cannot be avoided. Uh, in fusion-based AM processes, this is of course true. What we can do is we can have some post-processing stress relieving type steps to decrease the magnitude of these residual stresses, but they cannot be say eliminated or avoided altogether. Tensile residual stresses are preferable as they inhibit crack growth. This is wrong because if there are tensile residual stresses in a part, then it will tend to open up any pre-existing crack and it will make the crack propagate even further. So they cannot be preferable. On the other hand, compressive residual stresses are preferable because they will have the reverse effect and they will inhibit crack growth. And because of this reason, compressive residual stresses are preferable and less dangerous than tensile residual stresses. So options 1 and 3 are correct for the question. Option C is the correct answer. What is the disadvantage of using a robotic manipulator as compared to a multi-axis table for manufacturing supportless structures? Because remember, while both of these can be used for multi-degree of freedom, multi-kinematics deposition, there is some nuanced difference between the two. Is it that the robotic manipulator will have less degrees of freedom? Is it that process parameters may be different for non-overhanging and overhanging parts in the same build? Is it the difficulty in maintaining inert environment, or is it the smaller build volume? Let us go from bottom to top. Robotic manipulator, in fact, may typically have a larger build volume than a multi-axis table, and so option D is not correct. The difficulty in maintaining inert environment may be similar for both the cases because even with robotic manipulators, we can confine it to a chamber or have some shroud or cover to maintain the inert atmosphere. So this is not really true. The process parameters may be different for non-overhanging and overhanging parts in the same build. This is correct because, as we saw, there may be certain regions of a part where the deposition may take the form of overhead welding, in which case typically the process parameters can be very different from just a regular weld. Whereas in the case of a multi-axis table, the deposition head will always be perpendicular to the, or if you want to deposit at a tilt, it will always be at a specified angle to the pre-deposited layers, and so the process parameters will always be the same. Does it have fewer degrees of freedom? No, this is incorrect. In fact, sometimes the robotic arm may have more degrees of freedom than your multi-axis table. So option B is correct. Why are hardness values for the first few layers of a component deposited by MIG-WORM nearly constant? So we already discussed this in depth during the lecture, and I also showed you that demonstration on solid state thermal cycling. So this should be fairly easy. The first few layers undergo thermal cycling, leading to coarse microstructure and low hardness. First few layers undergo thermal cycling, leading to fine microstructure and low hardness. First few layers undergo thermal cycling, leading to coarse microstructure and high hardness. And first few layers undergo thermal cycling, leading to fine microstructure and high hardness. So all of them mention thermal cycling anyway. So we cannot eliminate any options based on just that. But what we can eliminate them is on the effect of thermal cycling that they promote. Option D says that thermal cycling will lead to finer microstructures and higher hardness. Thermal cycling will tend to increase the grain size, and thus it cannot lead to finer microstructures. It will lead to coarser microstructure, true, but a coarse structure will have lower hardness as per Hall-Pitch relationship, and so high hardness cannot be obtained with a coarse microstructure. Again, thermal cycling will not lead to a fine microstructure, but thermal cycling will lead to a coarse microstructure, and the process structure property relationship will be such that this coarse structure will lead to lower hardness, and so option A is correct. That is why the hardness in the first few layers will be lower than the layers towards the top along the bell direction. Why should we use non-organic piping in the context of MIG-WORM? Is it for lower cost? Is it because of less reactivity with common build materials deposited by worm? Is it to prevent process-induced porosity in the deposited part? Or is it because non-organic piping produces gases which, when subjected to high temperatures, assist in the WAM process? Will non-organic piping have lower cost compared to organic piping? We do not really have an objective answer to this, and even then, the cost of such piping will only be a very small contributor to the overall part cost for any parts which may be built by the warm process. So it will not be a say deciding factor. Is it because of less reactivity of non-organic piping with common build materials deposited by worm? The common build materials deposited by worm would typically include metals and alloys in wire form, and because of the considerably lower specific surface area of wires compared to powders, they may not have as much reactivity with either organic or non-organic piping materials. So this does not appear correct. Does it prevent process-induced porosity in the deposited part? Yes, it does, as you also saw in the slides, and as Professor Kapil explained during the lectures based on his own experiences and his own experiment. So C is definitely correct. And do these non-organic pipings produce gases at high temperatures which assist in the warm process? This is not the case. So option C is correct. Okay, question 8 onwards deal with electron beam wire arc additive manufacturing, which we did not cover today. So we'll be looking at them next week. And with this, we have come to the end of the present session. I thank you for tuning in to the live sessions for the course on fundamentals of additive manufacturing technologies. This was week 8. I hope to see you again next week. Thank you.